Let's move straight into Chapter 7, which is the dimensional analysis and modeling. Here's a scaled model of a U.S. Navy fleet destroyer and how it's being tested and introducing you to the Froude number, things like that. But this is showing you that you can have more than one way of modeling, right? So we've talked a lot about CFD modeling, and we talked a little bit and introduced a little bit into physical modeling. But this is another good way of testing the fluid effects or the fluid dynamics on some of our man-made items. Here's our objectives. So we've harped on this, so this is going to be quite a bit of overview, so we're going to go through it pretty quickly. A dimension is a measure of a physical quantity without numerical values. And then a unit is a way to assign a number to that dimension. There are 7 primary dimensions, also called fundamental or basic dimensions. These are the ones that we use the most: mass, length, time, temperature, electric current, so you've got watts, amps, things like that. And then the amount of light, and then the amount of matter. All non-primary dimensions can be formed by some combination of the 7 primary dimensions. So you can think of it like the primary colors. You have 3, and then you can take those and form the secondary dimensions and so forth. Here's force. Force equals mass over length time, which is so mass times acceleration. So you see here, a dimension is a measure of a physical quantity. So you have length, right? Because there's no numerical value there. You have a dimension, which is a length, and then you have a unit, which is a way to assign that. Here you have primary dimensions, so again, mass, length, time, etc. And then you have the unit, so kilogram, meter, centimeter, things like that. The law of dimensional homogeneity, we talked about that. I mentioned it first video, right? Every additive term in an equation must be the same dimensions. And that's because you can't add apples to oranges, right? So they need to be the same. These are homogeneous. This is not. So you can't get this. You know what you would get? You would get 2 apples plus 1 orange because they don't have the same dimension, right? Here's just different equations here. You can see this a lot in the Bernoulli equation, and we've already introduced the Bernoulli equation, but you can see it's a good example of dimensional homogeneous equation. All additive terms, including the constant, have the same dimensions, namely that of pressure, right? So non-dimensional equations, if we divide each term in the equation by a collection of variables and constants whose product has the same dimension, has those same dimensions, the equation is rendered non-dimensional. So if you have a non-dimensional equation and then you put all of those together, you're still going to have a non-dimensional equation. Normalized equation is the non-dimensional terms in an equation are in order unity, and the equation is normalized. Each term is a non-dimensional equation, is dimensionless, right? So then you have non-dimensional parameters. In the process of non-dimensionalizing an equation of motion, non-dimensional parameters often appear. The Reynolds number, the Froude number, things like that. We've talked about these. Hey, this doesn't have a unit because it's non-dimensional or dimensionless. The process is referred to by some authors as inspectional analysis. In most of these, the non-dimensional or dimensionless will have just 1. They'll just equate to 1. And so therefore it's just dimensionless. Equation of motion, dimensional result, dimensional variables, dimensional quantities that change or vary in time. Examples are z, which is dimension of length, and t, which is dimension of time. And so then we have non-dimensional or dimensionless variables, and those are quantities that change or vary in a problem, but have no dimensions. Angle of rotation measured in degrees of radians, dimensionless units. dimensional constant, gravitational constant g, while dimensional, remains constant. Parameters refer to the combined set of dimensional variables, non-dimensional variables, and dimensional constants of the problem. So just parameters, right? And then pure constants, the constant 1 over 2 and the exponent 2 in an equation. Other examples of pure constants are pi and e. And so we know that there's a few others, but the main ones that we use are pi and e. To non-dimensionalize an equation, we need to select scaling parameters based on the primary dimensions contained in the original equation. And so here we have an example here, and then we have a Froude number. And so that's the introduction of this. We're going to talk more about this, but this is very important. Okay, so in a typical fluid flow problem, the scaling parameters usually include a characteristic length, a characteristic velocity, and a reference pressure point, PO, less P infinity, whatever that ending point is. Other parameters of fluid properties such as density, viscosity, and gravitational acceleration enter the problem as well, and we will work through those. And so here we're talking about the Froude number. It is very important in free surface flows, such as flow in open channels. Shown here is flow through a sluice gate. The Froude number upstream of the sluice gate is FR1 equals V, it's just the equation, and it is F2 downstream of the sluice gate. And so what I want you to know is that you have the Froude number, and a lot of the ways that you can see it in normal life is if it is greater than 1, equal to 1, or less than 1. And so if you've ever seen a boat or a duck or anything trailing a free surface flow or just an open amount of water, and they're kind of leaving a wake behind them, then that Froude number is greater than 1. And here we briefly talked about advantages of the non-dimensionalization of an equation, but we never really went too far into it. But here are the two key advantages. Relationships between key parameters in the problem are identified. So when you have non-dimensionalized or non-dimensionalization of an equation, then you're better able to see and identify the relationships between key parameters, right? And then the number of parameters in non-dimensionalized equations is less than the number of parameters in the original equation, so it's just less to deal with. So those are the two main advantages. So here, in a general unsteady fluid flow problem with a free surface, the scaling parameters include, we talked about this, length, velocity, frequency, and a couple of other ones, pressure, things like that. Non-dimensionalization of the differential equations of fluid flow produces 4 dimensionless parameters. We get the Reynolds number, the Froude number, the Schroll number, and the Euler number. Okay, and so here they are. We have Reynolds, we have Froude, we have Schroll, and then we have Euler. So we also spoke about the benefits of doing CFD or a CFD analysis. And we talked about one of the main things is you get to design it, test it, and get out, well, as many kinks and information as you can out of a CFD analysis before actually taking it to a physical scale, because then that takes time, money, lots of things, and possibly re-engineering, retesting. You know, if you think of a car, if you're building a car, well, then you're going to do a lot of CFD analysis on that, because how many times do you want to crash this car, right? The least amount possible. It's because you're building an entire car, right? So once you progress past that CFD analysis, because you can only get so much, it's quite a lot that you can get out of a CFD analysis. But once you have exceeded that, the next step, and in most ones here to save time and money, you do a geometrically scaled model rather than a full-scale prototype, right? So you do CFD, typically you do CFD analysis, and then you do a scaled model, and then you move on to a full-scale prototype. So here, in such cases, care must be taken to properly scale the results. We introduce here a powerful technique called dimensional analysis. So here are three purposes: to generate non-dimensional parameters that help in the design of the experiment, to obtain scaling laws so that the prototype performance can be predicted from the model performance, and to sometimes predict the trends in the relationship between parameters. And so one here, or really all three, right? I want you to think of if you have a certain material, right? And it's easy to think of something like an alloy, like a steel, aluminum, something like that. But if you have some other type of, maybe a polymer, some kind of conjoined plastic that has a really great tensile strength or shearing strength, right? You have great performance, but only under a small surface area, right? But once you scale that out on a large sheet and you get very large stresses acting upon it, maybe it's not proportional, right? Maybe it's not going to perform the same. So here you want to obtain scaling laws so that the prototype performance can predict the model performance, so that you can identify those trends, so that you can generate the physical, numerical, and reporting of the results for the experiment, so that you can make sure that your scaled model is going to perform just as well or the exact same as your full-scale prototype. Here's the principle of similarity. So you have geometric similarity. The model must be the same shape as the prototype, but the scale by some constant scale factor. So you can see 1/10 scale, 1/12 scale, 1/5, i.e. whatever is appropriate for your experimentation. Kinematic similarity, the velocity at any point in the model flow should be proportional by a constant scale factor to the velocity at a corresponding point, right? So you want it to be the same as the prototype. You want to have it under the same conditions, under the same environment. And then dynamic similarity, when all forces in the model flow scale by a constant factor to the corresponding forces in a prototype. Force scale equivalency. So you just want the same environment, the same forces, the same geometric similarity, the same dimensions, all of these things, you want it to be the same, just on a scaled number, right? That's what you want. This is incredibly important and incredibly easy to make a mistake. Incredibly easy. For example, in '99, NASA had launched this Mars orbiter, Mars climate orbiter, to inspect the climate of Mars. And after 10 months of performance, it just broke apart and failed. And it was all because someone didn't use the correct homogeneous units. That's the whole reason. One person made a math mistake. It was a $200 million math mistake. So here you have a prototype and you have a model, and so you can see that these are scaled, but we're still producing, we're still putting velocities into it. We have the same scaling. It looks the same, just smaller. And you see this kinematic similarity. And that is achieved when all the locations, the speed, things like that, they're all proportional, they're all flowing. And so you see that you have these forces here that are similar, right? They're not going to be exactly the same. We know that it's not going to be exactly the same, but it's going to be similar enough to know that it's going to perform as well as the prototype. Okay? So here we use the Greek upper letter pi to denote non-dimensional parameters. In a general dimensional analysis problem, there is these two eyes, and we call the dependent pi giving the notation pi1. And then the parameter pi1 is a general function of several other pi's, which we call independent pi's. And here's a functional relationship between the two. And then we can ensure similarity as well. So here is another model car versus a prototype car and the geometric similarity, right? So it's being scaled down. And then here we're introducing the Reynolds number, and it's the most well-known and useful dimensionless parameter in all of fluid mechanics. This is it, and it's denoted by RE. Okay. And so here, the Reynolds number RE is formed by the ratio of density, the characteristics of speed, and the characteristic of length to viscosity. So, or you can use the ratio of characteristic speed, length, so velocity, length, over kinematic velocity. And so here again, we have the prototype and the model. And we have special cases, of course. They're all special cases. And it's mostly in aerodynamic drag force, okay? So for the special case in which the wind tunnel air and the air flowing over the prototype have the same properties and under the same conditions, the aerodynamic drag force on the prototype is equal to that on the scale model. If the two fluids do not have the same properties, the two drag forces are not necessarily the same because they do not have that similarity that we're looking for, even under dynamically similar conditions. So this is just showing you that while you can have dynamically similar conditions, you also have to take into account the properties. So this is a great slide to show how you can achieve similarity using different or non-appropriate fluids in what you would logistically use to test something just by using similarity, right? And so here is a water tunnel is used instead of a wind tunnel to test 1/5 scale model. The water tunnel speed required to achieve similarity is here, and the advantage is that the speed is much lower. The required speed is much lower than the required speed of a wind tunnel using the same size model. So you're using different working fluids, right? So the water tunnel versus the wind tunnel, but you can use different speeds, other ways of achieving that similarity with the environment to still have the item or whatever you are testing achieve the same results or get not the exact same, but very similar results that you can work with, right? So similarity can be achieved even when the model fluid is different than the prototype fluid. Here, a submarine model is tested in a wind tunnel. Water tunnels are very expensive, right? They are costly to build, costly to maintain, costly to continue to fill, to test, just everything that goes along with it. So if you can adjust the numbers, adjust the velocities, adjust those things in a wind tunnel to test those items that would need to go in the water, then that's a great alternative, especially for extremely large prototypes, right? Because could you imagine testing an extremely large thing that needed the water? You would have to have a very large water tunnel. They exist, but they're going to be, by and large, less than a wind tunnel. So here's the method of repeating variables and the Buckingham pi theory. So here it just goes into steps. So how to generate the non-dimensional parameters, i.e. the pi's. And so step 1, list the parameters in the problem and count their total number. Step 2, list the primary dimensions of each of the n parameters. Set the reduction j as the number of primary dimensions. Calculate k, the expected number of pi's, so k equals n minus j. Choose j repeating parameters. 5, construct the k pi's and manipulate as necessary. And then 6, write the final functional relationship and check your algebra. So it's just 6 steps. Here's the 6 steps again. And here is the step. So you see number 1, list the relevant parameters. You have 5, right? And so then you have step 2, you list all of these. So you have Z, T, WO, ZO, and G. Okay? And so here you have these. See? And then you can reduce. So J is 2, K is N minus J, so 5 minus 2 equals 3. The repeating parameters are those two. And then step 5, you work it all the way through here. It looks like a lot of math, and it is, but it's a lot of small math. So you see dependent pi, dimensions of pi 1, time, length, XYZ, second pi, dimensions of pi 3, things like that. So it's just breaking it down. And then here is mathematical rules that are great for adding, subtracting components, XYZ. Hence, it's wise to choose common parameters just because it's easier, like length, velocity, mass, density, things like that. And then here, you've made the name a non-dimensional parameter after you. Wow. So established non-dimensional parameters are usually named after a notable scientist or engineer. If you come up with one, let me know. We'll name it after you. And then finally, you get to step 6, which is the relationships between the pi's, and then the final result of the dimensional analysis. So are your pi's dimensionless? The method of repeating variables cannot predict the exact mathematical form of the equation. And just a quick check of your algebra is always wise, just because you can see here, even though it's really short, I mean, you know, this is not difficult math for us to work through, right? But it's a lot of it. And then caution, choose your repeating parameters wisely, because oftentimes when performing the method of repeating variables, the most difficult part of the procedure is choosing the repeating parameters. With practice, however, you'll learn to choose these parameters wisely because you'll be working with them. So a parameter that is already dimensionless becomes a pi parameter all by itself, like an angle, is already a dimensionless pi all by itself, and we know this pi without doing any further algebra. So here you have the Darcy friction factor and the Fanning friction factor, and although the Darcy friction factor for pipe flows is most common, you should be aware of its alternative. The Fanning, it is less constant, but the relationship between these two are these. So here, when we're talking about equations, we use the CFD, and we can validate some of these equations. And we can do that by predicting the velocity profiles and the values of wall shear stress for two physically different but dynamically similar pipe flows. So we've got air at 300 K following all of this, and then water at 300 K following all this. You can see that it's different speeds, things like that. The two pipes are clearly geometrically similar since they are both round pipes, right? Geometrically similar. They have the same average roughness ratio between the case, and we carefully have chosen the values of average speed and diameter such that the two flows are also dynamically similar. But here you have the Reynolds air and Reynolds water, and going through, they are similar here. Of course, if you took it out to more decimal places, right, you would see a difference. So here is a depiction of these two differences performing similar under a CFD calculation. It's a wall shear stress and non-dimensionalized wall shear for fully developed flow through an air pipe and water pipe. And you can see that the X's or the crosses are water and the circles are air. And so you can see those points on this line performing the same. So one of the most useful applications of dimensional analysis, so of CFD, is designing physical or numerical experiments in the reporting results of those. So we talked about that. We use CFD or other types of programs to model and to experiment in a place where it doesn't take any material to construct it. It doesn't take any time to physically build it. It does obviously take time to model, but it's going to be, by and large, less time than it would to actually construct it. And then also, you can regurgitate the model. So you can save the model and run it under tons and tons and tons of experiments, and they do. They experiment on it a lot, and they change little things here and there. They tweak the design, they tweak the material, they tweak the forces, things like that, to see how the trends are set and how the material performs and the testing standards and things like that. So the setup of an experiment and correlation of experimental data. So if we consider a problem in which there are 5 original parameters, one of which is a dependent parameter, a complete set of experiments called a full factorial test matrix is included. So this testing would be 5 to the power of 4, which is 625 experiments. We talked about how they run many, many, many experiments. This is how you can calculate how many to run. If you're like, well, how many do I run? You can do a full factorial test matrix, right? And so that's where it is. So you have 5 original parameters, and 1 is a dependent parameter. So that's 5 to the power of 4. And so they're saying, hey, do a test matrix of 625 experiments. So assuming that 3 primary dimensions are represented in the problem, we can reduce the number of parameters from 5 to 2. So 5 minus 3. Non-dimensional groups, and the number of independent parameters from 4 to 1. Thus, for the same resolution, we would need to conduct only 5 to the power of 1, 5 experiments. So that's how you can reduce it down when you're talking about non-dimensional groups. And that's how those correspond to having things like dimensionless or non-dimensional groups, and understanding what independent versus dependent parameters are, and those types of characteristics here, because you would obviously want to have only 5 experiments versus 625 experiments. However, most big manufactured things are run through many, many more than just 5 experiments. But it is good to know what the max you would need is, and then what the minimum you would need is. So here, for a 2π problem, we can plot the dependent dimensionless parameter as a function of independent dimensionless parameter. The resulting plot can be either A, linear, or B, nonlinear. And in any case, regression and curve fitting techniques are available to determine the relationships between the pi's. And so here you can just see the linear one in A and the nonlinear one in B, and the trends that are developing. And so here, if we did have more than 2 pi's in a problem, 3, 4, XYZ, you can then use that test matrix to determine the relationships, right? And between dependent pi's and independent pi's, in many cases we discover that one or more of the dependent pi's has negligible effect, and then we can just remove it from the list of necessary dimensionless parameters. So if you know that some type of independent or dependent, and in many cases it's the dependent, right? If you notice that that is just not really affecting your testing one way or the other, then just remove it, because that's one less parameter that you have to include and focus on. So incomplete similarity, we've shown several examples in which the non-dimensional groups are easily obtained with paper and pencil through straightforward use of method of repeating variables. In fact, after sufficient practice, you should be able to obtain pies with ease, sometimes in your head or on the back of an envelope. Unfortunately, it is often a much different story when we go to apply the results of our dimensional analysis to experimental data. And that's why we still have to do experimental data. That's why you can't take something from a CFD situation and just power through straight to a shelf product, right? That's why you have to do things like prototypes, scaling, things like that. You have to do actual experimental data. A problem that is not always possible to match is all the pies of a model to the corresponding pies of the prototype, because not everything is going to be the same, right? Even when you have that scaled model versus that prototype, not everything is going to line up perfectly because it's not the exact same thing, even if you are careful to achieve geometric similarity. And that is called incomplete similarity. Fortunately, in some cases of incomplete similarity, you are still able to extrapolate model test data to obtain reasonable full-scale predictions. That's because you're going to get a lot of data. You're going to get a lot of data about a lot of different parameters of the potential prototype, right? So even if your data in some capacities is not usable because of this incomplete similarity, that doesn't render it all incomplete. You will find a lot of similarities and you will be able to use those. Here's wind tunnel testing. So here's a moving belt. It's a semi, which is a model. So it'll be a scaled model. You have a velocity, you have some force, and you have a moving belt. And then you have a drag balance. Okay? And this is the measurement of the aerodynamic drag on a model truck in a wind tunnel. And it's equipped with a drag balance and a moving belt ground plane. And so that way it can simulate it moving on the ground, right? So you can illustrate incomplete similarity with the problem here, measuring that aerodynamic drag force. It's a 1/16 scale. It's geometrically similar to the prototype. It weighs 0.991, it's 0.991 meters long. And the wind tunnel has a max speed of 70 miles per second. The wind tunnel test section is 1 meter tall and 1.2 meters wide. To match the Reynolds number between the model prototype, the wind tunnel should run at least 429 meters per second. It's impossible in the wind tunnel. So here, so here's the formula for the Reynolds number, and here is the velocity. So you would go through here, plug in what you know, and then it spits out what you need to be similar. And you need 429 meters per second, but all we have is a max speed of 70 meters per second. It's not going to work. So what do? Well, you can use a bigger wind tunnel, and just a fun fact, they usually test with 3/8 scale model cars and 1/8 scale model trucks and buses in very large wind tunnels so that you can exceed and reach that number. You can use a different fluid. We talked about that with the air and the water. So you can use a different fluid for the model test. You can achieve a higher RE number, but that's typically more expensive because anytime you're using something more than air, it's going to cost, right? You could pressurize, right? You can do that, and then you can also adjust the air temperature. And that's to increase the maximum Reynolds number capacity. And then if you can't do any of that, you can run the wind test several times at speeds near the max speed and then extrapolate our results to the full scale Reynolds number. And so here, fortunately, it turns out that for many wind tunnel tests, the last option is quite viable. So that's nice that it's actually usable. So this is the one that we just talked about, just gave an example when we said, hey, even if some of the data is not usable, that doesn't mean, or even if some of the data does not render as matching to what your full-scale prototype would be, that doesn't mean that your data is not usable, right? It can still tell us things. You can still predict trends. You can still predict relationships between those, even if the actual numbers are not the exact same. So here, the Langley full-scale wind tunnel is large enough that full-scale vehicles can be tested. For the same scale, model, and speed, water tunnels achieve higher Reynolds numbers than wind tunnels. So you can use a different working fluid. And you can see it here. You can see those streamlines. You can see how turbulent this is coming off of the back. You can see drag force here. It's sticking to the car, right? And you can see this here as well. Right? You see lots of turbulence back there. So here, this is talking about the Reynolds number and how you get independence. So here, unreliable data at low RE, but the higher the RE, the higher the Reynolds number, the better the data. So for many objects, the drag coefficient levels off at Reynolds numbers above some threshold value. This fortunate situation is called the Reynolds number independence, when you kind of break out of that unreliable area. It enables us to extrapolate the prototype Reynolds numbers that are outside the range of our experimental facility. So that's saying if you don't have the access or ability to use that experimental facility, you can extrapolate the prototype Reynolds numbers. Here's flow with free surfaces. So for the case of model testing of flows on free surfaces, we talked about it, boats, ships, floods, river flows, all of this. Complications arise that preclude complete similarity, and that's because you're typically using a free flow surface, right? You're not making all of these pools, right? So here, if a model river is built to study flooding, the model is often several hundred times smaller than the prototype due to the limited lab space. You can't build a full-fledged river in your lab. I mean, technically you can, but you're not going to, right? Researchers often use a distorted model in which the vertical scale of the model, river depth is exaggerated in comparison to the horizontal scale. In addition, the model riverbed slope is often made proportionally steeper than that of its prototype, and these modifications result in incomplete similarity due to its lack of geometric similarity. Model tests are still useful under these circumstances, right? Even if your numbers aren't all the way correct, that doesn't mean that your data is not usable. Other tricks like deliberately roughening the model surfaces or empirical corrections and correlations are required to properly scale up the model data. So you can do other things to help offset that incomplete similarity. So here are ratios to kinematic viscosities to match both the RE and FR. And it's to ensure complete similarities, we would need to use liquid whose kinematic viscosity satisfies the equation. So you would need to get the right working fluid to satisfy the kinematic viscosity. And that's to achieve that complete similarity, right? We need to match what we need. In many flows involving a liquid with a free surface, both the Reynolds number and the Froude number are relevant non-dimensional parameters. Since it's not always possible to match both the RE and FR between model and prototype, we are sometimes forced to settle for incomplete similarity because complete similarity is difficult to achieve in some cases. Here you can see an airfoil being tested in a towing tank. Here's the FR numbers here, A, B, and C, proportionally. And in tests like this, the Froude number is the most important non-dimensional parameter. So here's a 1/100th scale model constructed to investigate navigation conditions in lower lock approach for 2 miles downstream of the dam. So you can see here, this is a dam all the way up here. This is the dam. There. So the model includes a scale version of the spillway, the powerhouse, existing lock, Navigation, so you've got the actual layout of what the geography looks like. So they're obviously trying to achieve this similarity, right? In addition to navigation, the model was used to evaluate environmental issues associated with the new lock-in required railroad bridge. So you can think of erosion, right? What it would do to local habitats or environments. The view here is looking upstream towards the lock-in dam. At this scale, 52.8 feet on the model represents 1 mile. On the prototype, a real full-scale pickup truck in the background gives you a better feel for this model. So it's enormous. This is an enormous scale. Here are many experiments involving free surface. We cannot match, again, both the Freud number and the Reynolds number. However, we can often extrapolate low RE model test data to predict high RE prototype behavior, right? So we can use, remember we talked about this, even if your numbers aren't right, we can do things like predict the behavior, predict trends, predict relationships, things like that, right? So if you see that something is increasing non-linearly, right? So non-linearly, and then right about here, it's starting to go in a linear fashion, then you can predict that that would continue, right, at the high RE number. So here is just a blurb that talks about how in Hollywood movies, they use quite a lot, right? Model boats, trains, airplanes, things like that. They blow them up, they burn them. And then when you have ones that don't look real or they just look unconvincing, right? That's because, or not all the way, but if the model's Froude number and Reynolds number differ too much in those prototypes, the special effects don't look right because you have seen these things in real life. You understand what a boat's wake looks like, right? You understand those things without even having to go through a fluids class. You may not understand it mathematically, you may not understand what that Froude number or that Reynolds number, but you know that if you put a boat in the water and make it go, you're going to have a wake, right? And so that's kind of the same thing. They pay attention to the dynamic similarities in order to make the small-scale fires and explosion appear realistic because you have seen things like that, right? So here's the summary. We went over dimensions and units, talked about the homogeneity that we need, dimensional analysis and similarities, method of repeating variables, Buckingham Pi theorem, and then experimental testing, modeling incomplete similarities, things like wind tunnels, flows, free surfaces, incomplete similarities. We went through all this, but now I'm going to show you a short video. It's about 10 minutes. And it gives a good overview with some actual, I won't say physical because you're watching it on a screen, but you will see some examples of these Froude numbers and RE numbers and what that means in things like a wake behind a moving body.
Dimensional analysis and similarity are very powerful tools in science and engineering. Before we use them, though, we need to appreciate the law of dimensional homogeneity, which states that every additive term in an equation must have the same units. In other words, you can't add apples and oranges. Consider Bernoulli's equation, for example. Static pressure P is a force per unit area with dimensions of mass over length times time squared. The dynamic pressure, 1/2 rho v squared, has to have the same dimensions. Adding the hydrostatic head z doesn't work because it isn't dimensionally consistent. However, we can instead express the head as a pressure, rho gz, and now it is consistent. Of course, the Bernoulli constant, or total pressure, must have the same dimensions of mass over length times time squared as all the other terms. This basic requirement of dimensional homogeneity naturally leads to a set of non-dimensional parameters that describe all sorts of fluid phenomena. By understanding the role of these non-dimensional parameters, we can learn a lot about fluid phenomena without actually having to solve the equations of motion. There are a lot of these non-dimensional parameters, but the most important one in fluid mechanics, which comes directly from non-dimensionalizing the Navier-Stokes equation, is the Reynolds number. It's defined as the ratio of the inertial force to the viscous force on a body, and it's equal to rho VL over mu, or just VL over nu. When the Reynolds number is much less than 1, as in this bead falling through shampoo, the flow is dominated by viscous effects. We call this creeping flow. When it's much greater than 1, as in the case of this airplane, the flow is dominated by inertial effects. The Reynolds number is named for that great father of modern fluid mechanics, Osborne Reynolds. Another very important non-dimensional parameter is the Mach number, named for Austrian physicist Ernst Mach. It's defined as the ratio of the speed of a flow, v, to the speed of sound, c, and it determines a flow's compressibility. For example, cars usually travel at speeds less than 1/10 the speed of sound, where we ignore any small density changes and consider the flow to be incompressible. On the other hand, some flight vehicles break the so-called sound barrier and fly at supersonic speeds, or Mach number greater than 1. When the Mach number is around 1, as in this transonic wind tunnel test of a space shuttle model, small speed changes make a big difference in the flow pattern. This leads us to the powerful concept of similarity. We can test a scale model of a commercial jetliner in a wind tunnel, for example, and expect to get results similar to those of the full-scale aircraft, so long as we make sure that the Reynolds and Mach numbers of the model match those of actual flight. A lot of wind tunnel testing, and nowadays CFD as well, go into the design of a commercial jetliner. For many flows at low speeds, Reynolds number is the only important dimensionless parameter. As long as we match the Reynolds number of the model to that of the prototype, model testing can even be done using different fluids. For example, we can study the flow over a golf ball in a water tunnel, or the flow over a submarine in a large wind tunnel. Depending on the Reynolds number, some flows have different regimes with different flow patterns. The classic example is the flow over a circular cylinder, illustrated here using a soap film tunnel. At low Reynolds numbers, between about 4 and 40, attached vortices form behind the cylinder. Above about 40, we see the famous Kármán vortex streak, the alternate shedding of vortices from one side of the cylinder and then the other. This is named after another father of modern fluid mechanics, Theodor von Kármán. A CFD solution also shows Kármán vortex shedding in the same Reynolds number regime. Finally, when the Reynolds number reaches values above a few hundred, turbulence begins to dominate the flow pattern. Another dimensionless parameter, the Strouhal number, gives a non-dimensional frequency for such periodic flows. On the other hand, some flows don't change very much over a huge Reynolds number range. Here we've generated a toroidal vortex ring by injecting milk into a small aquarium at a Reynolds number less than 1,000. The infamous mushroom cloud from an atomic explosion is a similar physical phenomenon, only here the Reynolds number is at least several billion. Fluid dynamic similarity between the two is obvious by visual inspection. In liquid flows with free surfaces, the Froude number compares the speed of motion to the natural speed of gravity waves. A ripple tank demonstrates motion with a Froude number less than 1, equal to 1, and greater than 1. In the last case, surface disturbances are left behind, forming swept-back waves. This duck is swimming at a Froude number greater than 1, producing a similar wave pattern. There's a strong analogy between these liquid surface waves and shock wave phenomena in supersonic gas flow, where swept-back waves occur when the Mach number is greater than 1. The Froude number is also important in open channel flows, such as the spillway downstream of a dam. In this experiment in a water channel or flume, the fast-moving supercritical flow downstream of the spillway causes erosion of the riverbed. In this flow, the Froude number is the most important dimensionless parameter to match between the model and the full-scale spillway. The Reynolds numbers don't match, but it doesn't matter. Although we usually think of models as being smaller than prototypes, there are cases where it's more appropriate if the model is larger. It's hard to study the aerodynamics of a real fly, for example. It's just too small. Instead, a set of mechanical wings is tested in a tank of mineral oil. This mechanical fly is 100 times larger than a real fly, and its wings flap 1,000 times slower. So even though the dimensional size, frequency, and even the fluid are different, dynamic similarity is nonetheless achieved by matching the Reynolds number, the Struhl number, and a third parameter known as the reduced frequency. The Mach number is very small in this flow and is not an important parameter here. In this CFD simulation of a fly in flight, the actual scale and frequency of a real fly have been used as boundary conditions. It shows the vorticity being shed off the flapping fly wings. The scaling of the simulation is 1-to-1 with the actual fly, so all the dimensionless parameters are automatically matched. However, there are situations in which scale models are tested with CFD, like this simulation of waves hitting an oil platform. It was set up to predict a model scale flow in order to compare with data from an experimental model test. Here's another example in which a model race car is simulated as it would be tested in a wind tunnel in order to compare with scale model wind tunnel data. But sometimes actual race cars are tested full scale in large wind tunnel facilities, guaranteeing that the dimensionless parameters of the test match those of the race car on the track.